Okay, good afternoon everyone. So my name is Street Lei and I'm currently a research fellow at CREST, Center for Research on Engineering Software Technologies. And recently I also graduated from the same group, as you can see from the photo. And thank you very much, CREST, for organizing my graduation ceremony and also taking good photos, especially William. And today I would like to express my gratitude to CREST for organizing this wonderful CREST Software Security Symposium and inviting me to give a talk. So today I will be presenting about data-driven support for software vulnerability assessment and prioritization. And this is also the main focus of my PhD. So let's start. Coincidentally, when I was preparing this talk, cybersecurity has also become one of the hottest keyword and topic in the news following the Optus data breach. And people are so concerned about this incident because cyber attacks, as you may already know, can cause massive damage, ranging from leaking user sensitive data to causing huge financial losses of millions to billions of dollars. But have you ever wondered what actually causes these cyber attacks? It turns out that these cyber attacks are usually caused by software vulnerabilities or the security flaws in software systems. So if you remember, earlier this year, the Log4j vulnerability has taken the entire internet by storm. The reason is that this vulnerability can lead to catastrophic cyber attacks and affect millions of software systems around the world. And actually, this is just one example among thousands of critical vulnerabilities discovered every single year. So you can see how much damage these vulnerabilities can cause if we don't prevent and address them on time. So ideally, when a new vulnerability is detected, developers will try to address them as soon as practical. However, in practice, it's no longer that easy because developers usually need to handle many vulnerabilities nearly at the same time, especially in large-scale projects. And you already know that developers are very busy with many different tasks, so they won't have time and resources to address all of them at once. So here, a burning question arises. So which vulnerabilities among the detected ones should developers prioritize to fix, as not all of them are equally dangerous? And how to perform such prioritization? So that's where the vulnerability assessment comes into play. So before diving into details, I would like to mention that besides the term vulnerability assessment, there are also other terms being used in the literature or in industry. For example, vulnerability analysis, risk assessment, or security assessment, etc. But regardless of the term being used, it's important to understand where this step fits into a vulnerability life cycle. So essentially, vulnerability assessment and prioritization happen after vulnerabilities are detected to provide inputs for the remediation of these vulnerabilities. And now, in order to perform the vulnerability assessment for a vulnerability, the traditional way would be to first develop an exploit or a piece of code in order to leverage such security weakness to get access into a system and then evaluate how such an exploit can negatively impact the system of interest. However, this process, as you may already guess, is mostly done manually and also requires significant human expertise. Thus, in the literature over the last decade or so, there have been a rise in the effort trying to automate this process. Specifically, many of the recent studies, in order to leverage the large-scale historical vulnerability data in the wild, they have developed data-driven approaches, for example, machine learning, deep learning, and natural language processing, in order to make use of such large-scale data, in order to predict these assessment outputs automatically. So the workflow I'm highlighting here actually introduces a new area called data-driven vulnerability assessment and prioritization. And that's also the main focus of my PhD. So specifically, my PhD has provided insight into the current practices as well as the state-of-the-art approaches in the field. And during my PhD, I have collaborated with many other researchers in order to develop a wide range of data-driven approaches in order to address 3 key challenges that hinder the practical applications of this area. So in brief, the key technical contributions of my PhD include, first, addressing the concept drift or the data changing issue when we want to automatically assess the vulnerabilities in the wild. The second contribution focuses on automatically assess the vulnerabilities early by leveraging the source code directly. And last but not least, in my PhD, I have also distilled real-world developers' needs in order to support automated, customized vulnerability assessment. But due to the time limit of today's presentation, I will just focus on the key theme of my PhD, which is about automating the task in this area. And the research in my PhD has resulted in 6 publications, as you can see on the screen, and most of them are published in top venues, A star according to the core ranking. But among them, as I mentioned, I will be focusing on the automated commit level vulnerability assessment because it aligns with the most common theme in my PhD. So the selected study title is Deep CVA, Automated Commit Level Vulnerability Assessment with Deep Multitask Learning. And this work was accepted into the International Conference on Automated Software Engineering, ASC, in 2021, which is an A-star venue. And this work was authored by me, David Hin, Roland Croft, and Professor Ali Barber from the University of Adelaide, and it's also partially funded by the Cybersecurity CRC. So in this study, the key goal is to develop a novel deep learning model, namely Deep CVA, to enable developers to prioritize and address vulnerabilities earlier and more efficiently compared to the existing techniques in the literature. So first, I would like to give you a bit more context for this study. Currently, in order to prioritize the vulnerabilities, researchers and practitioners are using a well-known framework called Common Vulnerability Scoring System, or CVSS in short. So essentially, CVSS provides various metrics to quantify the exploitability, impact, and also overall severity of vulnerabilities. And in practice, all of these metrics are useful to perform the vulnerability assessment to prioritize the vulnerability fixing. And as I mentioned earlier, data-driven approaches have been widely used to automatically predict these CVSS metrics. Specifically, many of the recent studies have leveraged the vulnerability description or reports in large-scale vulnerability databases like NVD, National Vulnerability Database, in order to determine one CVSS metric at a time. However, according to our analysis, we found out that the reports being used for the current assessment approaches are not published close to when the vulnerabilities are first added into a project as part of code commits. And by investigating further, we found that the time gap was actually more than 1,000 days, or 3 years on average, which means that it will leave many software systems open to cyber attacks for a very long time. So here, another important question arises: how we can bridge this time gap to enable developers to perform the vulnerability assessment earlier, or just in time when the vulnerabilities are actually injected into a code base. So in order to address this research gap, we propose to shift the vulnerability assessment from the report level to the commit level, where the vulnerabilities are first added into a project, which in turn also supports earlier fixing prioritization for these vulnerabilities. And moreover, we observed that the CVSS metrics, which are our main assessment output, can also be related. For example, a highly severe vulnerability would likely have high exploitability and impact values, and vice versa. Therefore, we investigate the possibility of predicting all CVSS metrics simultaneously in a single model in order to reduce the training and maintenance time, which is much more efficient compared to having separate models for individual metrics. And in order to fulfill these two aims, we propose DeepCVA, a novel deep learning model, in order to automate commit-level vulnerability assessment using multitask learning. So in this slide, I would like to just highlight the three main components of our proposed DeepCVA model. The first component is called hunk and context extraction, which mainly extracts the raw data from the input code changes. By input code changes, I mean the deleted and added code in vulnerability contributing commits, or the commits that contain the vulnerable code changes. And then such extracted input will be fed into the second component, which is a shared feature extractor. And this feature extractor consists of a three-way convolutional neural network connected to attention-based gated recurrent units. And the main responsibility of the second component is to extract the n-grams and their sequential order from the input code. So essentially, just extract the features that can be used for training the models. And last but not least, we have the multitask learning component, in which we use the multitask learning layers, which share weight, to enable the prediction of 7 CVSS metrics simultaneously. So now I would walk you through the key research questions that we investigated and the respective findings. So in research question 1, we compared the proposed DeepCVA model with various baselines, and these baselines have been developed based on the existing report level vulnerability assessment or other commit level tasks. So here I would like to present the key result based on the Matthews Correlation Coefficient MCC metric, as well as the data curated from more than 200 real-world software projects. So from extensive experiment, we found out that DeepCVA outperforms the best baseline by 38% on average. And if we only consider the best run of DeepCVA across different runs, because as you know, for deep learning models, the common practice is to run it multiple times, because each time we run it, the result may be different. And if we do that, the improvement further increases up to 60%. So overall, we found that all output or multitask learning is better than single task and unsupervised learning counterparts. And if you remember in one of the previous slides, I mentioned that DeepCVA contains multiple components. So in the second research question here, we evaluate the contributions of such components to the overall model performance. So in order to do so, for example, if we want to evaluate the contribution of a single component, we first remove it from the model and then combine the part before and after it to create a new model. And then after doing the experiments, we figure out that all the components have a positive impact on the overall model performance. And here I just want to highlight that in the shared feature extractor, we found out that using all the components together is better than using them separately. And we also found that multitask learning does not only improve the effectiveness, as I have shown in research question 1, but it also increases the efficiency by more than 6 times. And here are some of the key takeaways of the study I just presented. So we proposed DeepCVA, a novel model, in order to make the first progress towards just-in-time vulnerability assessment to support earlier fixing prioritization for vulnerabilities. And with the demonstrated effectiveness and efficiency, DeepCVA has moved one step closer towards our vision of having a unified and reusable solution for tackling relevant tasks to address vulnerabilities earlier. And besides all the contribution in my PhD, there's still many research opportunities existing in this emerging area. I mean the data-driven vulnerability assessment and prioritization. And I believe that most of these future opportunities are also applicable as extensible to data-driven software security in general as well. That's why in the last part of my talk today, I would like to briefly touch upon a few of these future directions in the area. So first of all, we have found many issues and deficiencies with the current data being used to develop the prediction models. So the first issue we observe is with the data size. I mean, like, the data size in this area is much more limited compared to other domains. For example, if you take the computer vision domain, you have the ImageNet datasets that contains millions of images. However, if you look at the vulnerability domain in particular, the data size usually ranges from a few hundreds to a few thousand, which is much smaller. And such small data set size would limit the model ability to learn any meaningful patterns. And in order to address this data size issue, I think that the semi-supervised learning or self-supervised learning, which are the current state-of-the-art approaches in other domains, can be investigated. Another issue we observe related to data availability and quality is that there are many different types of noises in the data we are using to develop the prediction models. And most of these noise is due to either manual labeling error or insufficient knowledge at the labeling time. For example, we cannot guarantee the absence of vulnerabilities in source code because we haven't had a perfect security testing oracle. What I mean is that you probably have seen like new vulnerabilities are constantly discovered over a year for the same components that have been developed maybe a long time in the past. So in order to avoid using such noisy data, or sometimes we just call it garbage in, garbage out phenomenon, then it's better to perform proper data validation and cleaning before actually using such data for the downstream analysis and developing prediction models. And now moving on to the second future direction in this area is to move beyond the traditional tasks in order to make the predictions more practical or useful for practitioners. So in this direction, the first thing we can consider is just-in-time prediction. What I mean is that before actually performing the prediction, we should consider whether the predicted output of our models would be provided before it can be used for the next step. Otherwise, the value of such output would be limited. Let me give you an example. Like in the SE work that I just presented earlier, we found that the existing vulnerability assessment approaches are commonly performed long after the vulnerabilities are fixed, which is not really useful in practice because if you think about it, because vulnerability assessment is supposed to provide input for the fixing, but currently it's performed after the fixing. That's why we propose to shift the vulnerability assessment earlier to the commit level. And another concern regarding the model is about its interpretability, or why a model is making certain predictions. And without such interpretability capability, it's very hard to convince end users of the model to trust the predictions or make use of the predictions to improve their process. For example, they don't know when the model would perform poorly so that they can invest more effort into that part of the process. And recently, there are also increasing worries or concerns about the models being poisoned by adversarial data, or called evasion attacks, because currently most of the effort has been invested into improving the model performance. But I think that moving forward is so equally important to pay attention to and invest effort into making the model more robust against adversarial attacks. And lastly, nowadays people are talking about AI-based systems, which means the systems that are powered by artificial intelligence and also massive data. And there are already many studies pointing out the differences between AI-based systems and traditional systems. which also leads us to believe that there are certain differences between these two systems in terms of the security as well as the vulnerability aspects. That's why we need to do more study in order to investigate whether, to what extent the current characteristics of conventional vulnerabilities are applicable or extensible to those in the AI-based systems. And another thing we observed is that there have been a lot of studies about adversarial attacks, but actually there are very few public vulnerabilities have been reported for these AI-based systems in the public databases like NVD. So we can see that with very limited amount of data, it's very hard to develop any useful data-driven approaches in order to detect, analyze, and fix the vulnerabilities for these emerging type of systems. And it's also worth noting that the AI-based systems involve or require not only the source code as in the traditional systems, but also require data to train the models as well as the trained models themselves. And each of these artifacts can also contain like security flaws or vulnerabilities as well. So it's very important that we need new mechanisms to integrate all of these artifacts when we perform the vulnerability assessment for these AI-based systems. And this also brings me to the end of the presentation today. Thank you very much for your attention. Now, if you have any questions, I will be happy to answer.
Question or trade?
I have a suggestion. When I see this type of knowledge building with neural networks, they are based on past experience. Essentially, you feed the patterns of these vulnerabilities. However, if there are some completely new classes of vulnerabilities that were never met, they will never be identified.
Yes.
So I suggest if you focus on the predictions that it failed rather than confirming the success, if you observe whether those failures are because of this reason. This is something conceptually new, it wasn't in the previous knowledge. Perhaps you can detect why the failure is occurring.
Yes. Thank you for the comments and suggestions. Actually, the thing you just mentioned kind of aligns with the model interpretability issue that I just presented, like why, for example, if the model say that this artifact or this piece of source code is vulnerable, why is it the case? So currently, as far as I know, this kind of information is not very evident in the current literature. And another thing is that we can consider the thing you mentioned as an anomaly detection problem. Like instead of saying like whether it's vulnerable or not, we kind of try to figure out the common patterns of the vulnerabilities. And then if something new comes and it doesn't share similar patterns, then it may be considered as anomaly. So that's a potential solution to address like new types of vulnerabilities.
And for the wrap up, we can also talk about the zero-day attack, because I think we should also think about Optus was zero-day attack, or it was actually very well-known vulnerabilities, leaving the API open kind of thing. So prediction models are not good for zero-day attack, what you mentioned, right? And I think, if there is some good thing to think that we also focus on the fail prediction models, because they can tell us a lot as well, which is interpretability. Any more questions?
Okay, good.
Go ahead. Whoever.
Okay. So the entire approach is based on data-driven approach, right?
Yes.
And you mentioned one of the weaknesses or feature direction was the availability of the security data, right?
Yes.
Imagine you do not have any data. Now, what is the trivial process of identifying this kind of vulnerabilities? Is there any knowledge base or any kind of any such kind of process where we can identify those vulnerabilities?
The thing you just mentioned is also the current problem for the AI-based system, because there are very limited amount of vulnerabilities reported for this new type of system. So in that case, it's quite hard to apply the data-driven approaches readily, because as the name suggests, we need the data in order to develop the models. So in that case, we need some kind of a head start by relying on the human expertise or the security experts' knowledge to identify a few examples, and then from there we can try to adapt the existing techniques developed for more mature domains and try to apply them into these